A very good morning, one and all. Today we are learning the subject of circuit theory or network analysis. So here we will see the chapter of the transient response. In the transient response, we have simplified in the previous lectures the numerical on the series RLC circuit. So today also we will simplify few remaining numericals on the series RLC responses. We will check here in the transient if we are going to connect the RLC circuit in series, what will happen, how we can see the change in the characteristics of the transient response in the what we can say the integral and the differential form, that we will see today. Few numericals already we have done and few are remaining, so that we will continue today. Introductory part already we have done. Okay, so this I'm not going to continue the introductory part which was already done in the last lecture. We will continue the numerical on the transient response. Fine. What are the what were the few what you can say the procedure, the steps, the initial conditions that we have seen. So in the last lecture we have solved the numerical on the RC. Now you just continue the numerical on the RL circuit, series RL circuit, numerical on the series RL circuit. So note down this numerical. RC is over. Now just go ahead for the RL. Series RC circuit already we have simplified. Now go for the series RL. Okay, so what is that? In the circuit shown below, the switch is closed at t is equals to 0. In the network shown below, the switch is closed at t is equals to 0 with a zero current. With a zero current in the inductor, find I, di by dt and d square I by dt square at t is equals to 0 plus. At t is equals to 0 plus. We have simplified this numerical. Just go through once again. So here switch is given. Okay, so the switch is open circuited switch and the R and the L is there which is connected in series. Current I of T is there. So be careful whenever you are going to simplify the numerical on the transient. We should consider the with respect to time period, that is nothing but the sources, that is I of t as well as the V of t likewise. So source is given the 100 volt and the resistor is a 10 and the inductor is a 1 Henry I of t. So at initial what we need to find out, that is at t is equals to 0 minus the current is flowing through the inductor. So at initially at particular t point, that is t is equals to 0 minus what will be my current, that is nothing but I 0 minus will be equals to 0. Definitely if switch is open and then no amount of a current will flow through that. So here at t is equals to 0 plus means after the switching. This is before switching. 0 minus is a before switching and 0 plus is after switching. The inductor will be act as open circuit, no doubt at all. See here, the inductor we need to redraw the equivalent circuitry of the given after applying the initial conditions, whether it's a short circuit or whether it's a open circuited inductor and the capacitor. We need to take care about that before going to simplify. So always remember the circuitry given circuitry, whether it's a given in the series or the parallel, whether the switch is open or the closed, whether it's a steady state or the transient. These things are very important. Later on you just start with the before switching and after switching apply the conditions and just do inductor and for the inductor and the capacitor open and the short circuited. Now go for the I is equal I at a 0 plus. So definitely that amount will be at initial, it will be 0. So whenever you are going to write the equation for the KVL, definitely already we have simplified many numerical related to the KVL. Okay, Kirchhoff's voltage law equations. So at whenever the time is increasing or after the switching, definitely current will be start to flow. So whenever t will be greater than the 0, how we can write the equation? So V minus IR is equals to 0 will be the condition. So V is 100 minus IR. I is will be as it is and the R is nothing but the 10 minus of for the inductor L into di by dt. What is L? L is nothing but the 1 Henry. So here is the 1 di by dt will be as it is equals to 0. So what is the here? How we can write that KVL? That is a V minus IR is equals to 0 that we need to apply here. So and you need to redraw the circuitry. So voltage we are applying, the current will be at a 0 plus after the switching and the resistor will be as it is, but the inductor will be treated as a open circuited. Getting? Now, so after this 100 minus 10i minus 1 into di by dt is equals to 0 will be the equation number 1. So now in the second case, how we can find after derivating, okay? So in the second case, whenever, so after differentiating, you can write there the after differentiating, the circuitry will be like this, because we are interested in the second step, that is after differentiating. So what will be the case? Di by dt is equals to, you just keep one side the di by dt, and the 100 minus 10i will be the equation number 2. Now at t is equals to 0 plus, at t is equals to 0 plus, what will be happen? Di by dt is 0 plus 100 minus 10 into I of 0 plus. Whenever there will be the I, you just convert that I into 0 plus. Whenever this is the I, again convert into the 0 plus. So then only it is possible to substitute the value. So 100 will be here, 10 into I 0 plus. So I 0 plus is nothing but again the 0. So this entire term will become as a 0. So what will left here? That is 100. So 100 ampere per second is nothing but my di by dt at 0 plus. So differentiating the equation number 2. Previously we have differentiated the equation number 1. After differentiating the equation number 1, we got di by dt. Second time, whenever we are going to differentiating, we are getting a d square I by dt square. We remember at initial 0 minus 0 plus, we got the current I, okay, in the both the cases 0 minus and 0 plus. Once we got that current, write the KVL, V minus IR equation, then differentiate that one. Okay, that first differentiation is nothing but di by dt. Second differentiation will be your d square I by dt square, okay, with the help of the equation 1 and 2. So here in the second time, for same equation, same is which one? This one. We are differentiating the equation number 2. You will get a d square I by dt square is equals to this one. So that is nothing but here. So this term will be 0, minus of 10 will be as it is, and this I will become as a di by dt. Now at t is equals to 0 plus. Why I am writing every time this condition? Why I'm writing this t? Because we need to apply, because at a 0 minus is the case is a different, and 0 plus is case is a different. At 0 minus before switching, but we are interested after switching. That's why I'm writing here the t is equals to 0 plus. So d square I by dt square, this case at 0 plus, at 0 plus. So minus 10 into di by dt will be as it is, but at 0 plus. So I need to apply here the value, because already I have calculated di by dt as 0 plus is nothing but 100. So that you need to apply here. You need to write here the value which you have got from here, that is 100 ampere. So this 100, so minus of 1000 ampere per second square, minus 1000 ampere per second square. So in this way we have simplified the numerical on RL, okay, transient series response of your the RL circuit. Transient series response of your the RL circuit. So now we will switch towards the parallel transient response of your the parallel circuitry, okay. So we are interested today now. The series is finished. The topic of the transient response of the series RLC circuit is finished. Now we will go for the transient response of your the parallel RLC circuit. Parallel RLC circuit. So here one by one we will see the three circuitry. One will be related to your the RL, that is the resistor will be connected in series with your the inductor. That response we will observe. Secondly, we will observe the RC, that is nothing but resistor will be connected in a series with your the capacitor. So that response we will observe, and at the end we will observe RL and C, that is all the three components RL and C will be connected in parallelly. Okay, so what will be the response of their transient, that we will observe here. So in the three cases are there, three numericals we will simplify. One is RL, the second is RC, and third is RL and C. So this is the transient parallel RLC RL circuit response. So the numerical number one will be, note down all of you. In the circuit shown below, in the circuit shown below, in the circuit shown below, at t is equals to 0, in the circuit shown below, at t is equals to 0, the switch is opened. At t is equals to 0, the switch is opened. Stop, calculate v comma dv by dt, v comma dv by dt, and d square v by dt square, and d square v by dt square, and d square v by dt square. If you observe the circuit, d square v by dt square at t is equals to 0 plus, at t is equals to 0 plus, we will remember in the series transient responses or the series circuit simply. So we were interested the amount of a current which is flowing through the entire circuitry, which was the same in the what we can say, the series circuitry. Okay, so in the series we have calculated the current, that is I comma di by dt comma d square I by dt square. These three cases we have calculated whenever the switch before switching and after switching cases, that is 0 minus as well as the 0 plus case. Whenever the t is equals to 0 minus or t is equals to 0 plus, or I is equals to 0 minus and I is equals to 0 plus. But if you are going to simplify the numerical on the basis of the parallel circuitry, so here we are interested to calculate the voltage. Okay, voltage drop across. Okay, so that voltage potential or the voltage we need to calculate here. How we can calculate? We need to calculate the v, we need to calculate the dv by dt, we need to calculate d square v by dt square. These three cases we need to calculate. So by observing the circuitry you will be able to find the current is of 1 ampere and connected parallelly, and the voltage is here the v of t. We are going to measure here after the switch, because once the at present the switch is open, but whenever the switch is going to be closed later on, we are interested to find out the potential at this moment, at this particular point. So L will be 1 Henry and your the resistor is of a 100 ohm. Getting? So this is the RL circuitry. So now apply the condition. What is that conditions? At t is equals to 0 minus. Why I am writing here the t is equals to 0 minus? Just because I am interested at present, at beginning, at initial, the before switching case. Okay. So t is equals to 0 minus, the switch will be closed. At t is equals to 0 minus. Okay, this is the first case. Now later on, the switch is closed. Just to do the switching, close the switching. So what will happen? Hence, no current flowing through the inductor. Obviously, no current will be flow through that inductor. So the current which is flowing through the inductor at a 0 minus will be the 0. But whenever you are going to close the entirely closing the circuit, what you can say, fully closing that switch. So what will happen at t is equals to 0 plus, the inductor will be act as an open circuit. Okay, the inductor will be act as a open circuited. So see here the equivalent circuitry of your the given circuit. After applying the initial condition, the inductor will be treated as open circuited. So see here the open circuited inductor and the resistor will be as it is. Okay, and here we are interested the voltage, that is a v at a 0 plus, and the current amount of a current which is flowing. So because later on no need to talk about this switch, the switch position will be the as it is, no doubt at all. But once we are going to close the switch, the role will be over. Okay, so now here at a 0 at t is equals to 0 plus, the inductor will be act as an open circuit. At that time, IL is equals to IL at a 0 plus is equals to 0. IL at 0 plus is equals to 0. That is nothing but the amount of a current flowing through the inductor will be at 0 plus will be the 0 just because of the open circuited. What will be the voltage? V is equals to IR. V is equals to IR. So V at a 0 plus is equals to IR. What is my I? I will be 1 ampere and R is nothing but the 100 ohm. See here. R is 100 ohm and the I is nothing but the 1 ampere. So in this way you will get V at a 0 plus is nothing but the 100 volt. V at a 0 plus is a 100 volt. Go for the next one. That is nothing but now the second step. What is that second step? Once the t will be start for the time period will be increasing. Okay, after the switching permanently. So what will be the case? The inductor will be as it is. The resistor will be as it is. Voltage drop across this one. Potential V of t will be there and the current is of 1 ampere. So apply just by writing the KCL here. Whenever you are going to simplify the numerical on the parallel circuitry, remember we are interested to write the equation of the KCL. Whenever you are going to simplify the numerical on the series circuitry, at the time just careful, we are writing the equation for the KVL, V minus IR is equals to 0, whereas in the KCL we are interested I is equals to V by R case, I is equals to V by R case, or you can say I minus V by R is equals to 0, I minus V by R is equals to 0, anyone you can take. So by looking at this equation you can identify this is the I is equals to V by R case. See here this entire circle is a V by R, but while talking about the only register, so V by R. But if you're having the L, either the L or the C, you need to add that component. So that's why here the additional components are mentioned. Otherwise, this is the I is equals to V by R case. But we are having the inductor, maybe the capacitor in the other numerical, or maybe the RLC in the other numerical. So depending upon the component placed in the circuitry, you need to add. But the thing is that we need to remember the important point is nothing but while write for the parallel circuitry, use the equation of yours, the KCL, write the equation of I is equals to V by R, okay, of the equation. And if you're simplifying the series circuitry, go for the KVL, V minus IR is equals to 0. So in this way, you can simplify easily, okay. So now just start with writing that KCL equation, how it is possible if once the switch is closed and the time it is increasing greater than the 0, obviously. So I is 1 is equals to V by R is V will be as it is and the R will be the 100 plus what is this case 1 by L integral of 0 to T V into dt. 1 by L integral of 0 to T V into dt. What is 1 by L? L is an inductor. Inductor value is 1. So 1 by 1 will be as it is 0 to T. The time is from the initial to the final, that is nothing but 0 to up to the T. So V dot dt is equals to 1. So this is the equation number 1. Differentiate this equation number 1. What you will get? What you will get? This 1 by 100 will be at one side. This V will become as a dV by dt. Okay, after integrating this one, you will get as only the plus of V. Okay, is equals to 0. So after differentiating the equation number 1, you will get as 1 by 100 dV by dt plus V is equals to 0. That is equation number 2. Okay, now what is the case? At T is equals to 0 plus. The procedure is same every time. We remember procedure is same every time. Keep in mind procedure are 4 to 5 that you need to apply. Once you remember the procedure or the step, it is very easy to simplify many numericals. You can simplify yourself. The steps, the procedures is important, what you are doing exactly. Step number 1 what you are doing, step number 2 what you are doing, 3 4 5 like that. Okay, now at a T is equals to 0 plus, what will be the case? What we are doing, we are again there differentiating. We are placing the t as a 0 plus. So in the first case also, what we are doing, dv by dt. Where is my dv by dt? This dv by dt at a 0 plus is equals to minus 100. Okay, how we got this is at one side, so it will be go at a left, what you can say, left hand side is there, but it will go right hand side, so it will become as a 100, and this v will be combined. So this 100 into v of a 0 plus. So what is my v into 0 plus? Already we have calculated in the previous slide. V 0 plus is nothing but the 100 again. This 100 and this 100, it will become as a 10,000 volt per second. Volt per second. So dv by dt at 0 plus is a 10,000 volt per second, minus 10,000 volt per second. Now that again differentiate the equation number 2. First we have done the differentiating the equation number 1. Differentiating the equation number 1. Now differentiating the equation number 2. 1 by 100 d square v by dt square plus dv by dt is equals to 0. So at t is equals to 0 plus is mandatory to write that condition. So d square v by dt square at a 0 plus, see here 0 plus 0 minus, this is mandatory to write because already we are getting that values. So here is a minus 100 into dv by dt of 0 plus. What we got the dv by dt 0 plus, that is a 10,000, that is nothing but 10 raised to the power 4. 10,000, that is nothing but 10 raised to the power 4, and that to minus 10,000. So here minus 10 raised to the power 4. So this minus minus will become as a plus, and this will be 10 raised to the power 6 volt per second square. Volt per second square. Volt per second square. Go for the next numerical, which is related to the transient parallel RC circuit response. So we are interested here, the resistor will be connected in series with your the capacitor. We are interested to find out the observe the response of your the transient of the parallel circuitry, of the parallel circuit. So note down this numerical. In the circuit shown below, the switch is opened at, in the circuit shown below, the switch is opened at t is equals to 0. In the circuit shown below, the switch is opened at t is equals to 0. Solve for dv by dt, solve for dv by dt solve for dv by dt and d square v by dt square and d square v by dt square at t is equals to 0 plus, at t is equals to 0 plus, at t is equals to 0 plus. So if you observe this circuitry, you will be able to find the R is connected parallel with the capacitor and switch is there, and the current along with the voltage source. So here we are interested dV by dt as well as the d square v by dt square at t is equals to 0 plus, obviously. So after drawing this circuitry, you will be able to find here, apply the condition at t is equals to 0 minus, the switch will be closed, hence the voltage across the capacitor will be the 0 at the beginning. At the beginning, the voltage drop across the capacitor will be 0, that is v 0 minus, that is equals to vc 0 minus will be equals to 0, getting the voltage, um, the main or you can say the potentials or the voltage, total voltage will be equals to capacity voltage will be equals to 0, both will be equals to 0. This voltage, which is the source voltage you can say, and the voltage across this capacitor, both are equals to 0 when the switch is closed at the instant when the t is equals to 0 minus. Similarly, whenever the t is equals to 0 plus, the capacitor will be act as a short circuited. So here will be short circuit, here will be short circuit, here will be the resistor, and here will be the current, that is of 10 ampere. V 0 plus, here will be the 10 ampere, V 0 plus, here is the R, here is the C. Okay. After when the t is equals to 0 plus, the condition is applied, V 0 plus will be 0. Write the KCL equation for the t is greater than the 0. T 0 minus is over, T 0 plus is just now we written. Now come towards the next equation writing, that is nothing but the KCL equation. Whenever the t is increasing, that is the time period is increasing gradually from the 0 to so its value, so that will be t is greater than the 0. So how we can write that equation, that is I is equals to v by r case. So here the not only the r is there, along with that r there is a capacitor, so we need to write here the equation for the resistor as well as the capacitor. So I is equals to V by of R as well as the capacitor value. So I is nothing but the 10 ampere I have written here. V by R, so V will be as it is. R is nothing but the 1000 plus C into dV by dt. How we can write the equation of the capacitor for with respect to the voltage? That is a C into dV by dt. Already we have done in the introductory part how we can write the equation of the capacitor, the inductor, if they are short circuit, if they are open circuit. Okay. So how they can write in terms of the current and the voltages, already we have seen. Same thing we are applying here at present. If L is there along with your the current, so L into di by dt. If C is there along with your the voltage, so C into dv by dt likewise. So here, so we divided by 1000. So where is the 1000? That is nothing but the resistor V by R. I is equals to V by R. I is nothing but the 10 is equals to V by R. V is into 1000 plus C is there, C into dV by dt. C is there 1 microfarad. So here will be the 10 raised to the power minus 6. Getting? So this equation is nothing but my equation number 1. Now go for the next. That is nothing but whenever you are applying again the t is equals to 0 plus. So differentiate the equation number 1. So what will happen? If you're applying, first of all note down the 0 plus everywhere. So v 0 plus 1000 plus 10 10 into 10 raised to the power minus 6 into dv by dt of 0 plus is equals to 10. After writing this this one 0 plus, just to do one side the dv by dt term. So dv by dt at one side at a 0 plus will be equals to dv by dt at a 0 plus is equals to 10 divided by this 10, this 10, this 10 divided by which one, the capacitor value. So what will happen? 10 divided by 10 raised to the power minus 6 will be here again. And this 10 into, so what you can do, you can, this denominator will go up in the numerator. So 10 into 10 raised to the power 6. So in this way you will get as a 10 raised to the power 7 volt per second. Now differentiating the equation number 1, what will be the case here? This equation, you need to differentiate this equation. So 1 by 1000 will be at one side, dv by dt will be at the other side, plus 10 raised to power minus 6 will be So d square v by dt square, this case is equals to 0 at t is equals to 0 plus. Once again, whenever you are having a dv by dt, just do it at 0 plus. This is also the 0 plus. This is 0 plus, this is 0 plus. Substitute the value of dv by dt at 0 plus, that is nothing but 10 raised to power 7. So here is also the same case. So you will get finally as d square v by dt square is nothing but minus 10 raised to the power 10 volt per second square, minus 10 raised to the power 10 volts per second square, volts per second square. So in this way we have simplified the RC circuit. Now go for the last, that is nothing but the RLC, are connected parallelly. So we can observe what will be the transient response of your the RLC connected parallelly. So what is that case? For the circuit shown below, the switch is closed at t is equals to 0. Determine v comma dv by dt and d square v by dt square at t is equals to 0 plus. In all the cases, the same similarity will be there only. The t is equals to 0, t is equals to 0 minus, and you need to find out all the calculation when the t is equals to 0 plus or t is greater than the 0. So in the simple way, I'm telling the statement is the common in throughout in all the cases. So what we need to do, the numerical will be on the t is equals to 0 or a t is equals to 0 minus. The switch will be the closed one, okay, open or the closed one depending upon that, and you need to calculate either the I di by dt or d square I by dt square, or v comma dv by dt or d square v by dt square, this case. So now here RLC circuitry is there. So R, L and C connected parallelly, and V of T across that to 2 ohm 100.5 microfarad, and the 10 ampere is there. So at T is equals to 0 minus, no current will be through the inductor. So there is no voltage drop across the capacitor. So current which is flowing through the inductor will be the 0. The voltage drop across the capacitor will also be the 0, just because of the initial condition, that is T is equals to 0 minus. At t is equals to 0 plus, the inductor will be act as an open circuit, capacitor will be the short circuit. Already we are aware from this condition. See here the open circuit and see here the short circuit. So if open circuit, the current will be 0. IL at 0 plus will be the 0, and the V, the voltage drop across this one, V at 0 plus will be the 0. Likewise. So if you're going for the next one, so same condition you need to apply. IL at 0 plus will be the 0, and V at 0 plus is also the 0. So whenever the time in increasing, that is t is greater than the 0, so what, how we can read out the circuit? 10 ampere R L and C, 10 R L and C, 10 ampere resistor, inductor and the capacitor, and we are interested to find out the voltage drop across that one, V of T. So just write the equation again, the KCL equation when the t is greater than the 0. See here again, the I is equals to V by R, I is equals to V by R plus V by L plus V by C, you can say. Voltage drop across the resistor, inductor, capacitor, like this. Resistor, inductor and capacitor, we are interested. I is equals to V by R plus V by L V by C. How we can write? V by R is nothing but V divided by R is nothing but the 2. For the inductor, 1 by L integral of 0 to 2 V into dt plus C into dV by dt for the capacitor. 1 by L 0 to t V into dt plus C into dV by dt for the capacitor. So at t is equals to 0 plus, substitute the value of 10 here, and the V at 0 plus by 2, and here will be the 0 case and the 0.5. Okay, here will be the 0.5 after integrating, and this will be the as it is as 0 plus. So finally you will get dV by dt at 0 plus is nothing but this 10 into 2 20, this 10 into 2 will multiply this 20, so 20 into 10 raised to the power, this become as a plus 1, that is a 6 volt per second. Differentiating the equation number 1, okay, what you will get as a 0, first term 0, so 1 by 2, this 1 by 2, this 1 by 2 dv by dt, this case dv by dt plus v will be as it is plus 0.5 into 10 raised to power minus 6, and this d square v by dt. Just mention here the equation number 1. Just mention here equation number 1. So this will become as 0, 1 by 2 dv by dt plus v will be as it is 0.5 into 10 raised to power minus 6 d square v by dt square. Substitute the value at a 0 plus, this 0 plus, this 0 plus, this 0 plus. So at the place of 0 plus, 20 into 10 raised to power 6, substitute. So you will get as this 6 as well as this 6, it will be go in the what we can say at addition. So you will be this 6 and this 6, it will become as a 12. So minus 20 to 10 to the power 12 volt per second square. So in this way we have tried to simplify the numerical on the basis of your the transient responses of your the RL, RC, RLC. when they are connected series, when they are connected in parallel. So the steps are common. What are that step we need to keep in our mind at the beginning? Always remember what we need to calculate. What we need to calculate in the whether we need to calculate the I comma di by dt comma d square I by dt square, or v comma dv by dt comma d square v by dt dt square. So in the current related three things, voltage related three things, this is the first one. Secondly, in which form the circuitry is mentioned, whether it's in the series form or whether it's a connected parallel, that is important. Third, uh, whether it's a RC, RL or the RLC, that you need to take care, whether it's a RC, RL or RLC, that you need to take care. Next, if it's series circuitry, apply the KVL. If series circuitry, apply the KVL. At t is equals to 0 minus, you can now start, then the t is equals to 0 plus, then t will be t is greater than 0, apply the equation v minus ir is equals to 0 and find out the parameters. Three parameters. The first at the initial, that is I, second is the what is the di by dt, then third is nothing but t square I by dt square, and the in the voltage, that is parallel circuitry is there. So again the 0 minus, 0 plus, t is greater than 0, apply the KCL and just simplify the numerical on the KCL. Okay, so in the KCL also I is equals to V by R. Simply R is there, then the V by R. If L is there, R and L is there, V by R and the V by L. If RC is there, then V by R and V by C. If all three together is there, so with respect to the resistor, inductor and the capacitor, writing the voltage equation. So here for the L is nothing but 1 by L integral of 0 to t v into dt. For the capacitor, C into dv by dt. Okay, vice versa case in the writing the equation for the current, that is L into di by dt, and 1 by C integral of 0 to 2 into I into di by dt for the capacitor. So these things are very basic things that you need to keep focus while you are going to simplify the numerical. Even you need to focus whether it's a transient response or whether it's a steady state conditions. In the steady state, no need of fear the we are not interested in the time period, that is nothing but the t. We are not interested in the 0 minus, we are not interested in the t is equals to 0 and the 0 plus, likewise we are not interested in any case. Okay, simply we are going to simplify the numerical and we are finding the sinusoidal or either the AC or the DC RLC responses of the steady state conditions. Okay, we are not interested at the T, especially while you are learning the transient. Definitely we are interested with respect to time period. We are interested in the differential and integral form. All these things we are interested to simplify the transient responses. So this was related to the transient response of your the RLC parallel circuitry. So this way I am going to stop here. So whatever the post is coming, so I request you all, many numericals are in the posted video. Just go through whatever the posted link is given to you. View that one, try to solve yourself, change the value and do the practice. So every time, instead of searching new thing, better way, you just